Now consider a capacitor in an AC circuit. In this case, it's not Ohm's law that's always true. It is this relationship between the voltage and the charge and the capacitance in a capacitor. Vc is equal to Q over C. Now, there is an expression we can write that's very similar to Ohm's law, which says that Vc max is equal to I max X sub C. X sub C, we define it as what we call the capacitive reactance. So this is a definition, and what X sub C equal to is 1 over 2 pi Fc. This capacitive reactance is going to have the units of ohms, the units of volts over amps, that's the unit of ohms. And essentially it's going to behave, for the max values, it's going to behave very similar to resistance. Of course, this equation is applicable for RMS values, or in other words, Vc RMS is equal to I RMS IC. Now, this is where the similarity with the resistances stop. Let's look at a simulation of the voltage and the current across the capacitor, across and through the capacitor. Notice here the current in red, the voltage in black. I reduced the frequency here so we can notice it. The current is actually at a maximum when the voltage is 0, and vice versa. When the current is 0, the voltage is at a maximum. In other words, we notice that the current and the voltage for a capacitor are not in phase. They are actually 90 degrees out of phase. And in this case, let me put it back, the voltage looks like it is behind the current. The current looks like it is ahead of the voltage. So the voltage across the capacitor lags the current. So if I graph it here, when the current is 0, Vc is going to be at a minimum. When Vc is 0, I is going to be at a maximum. When I is going to be 0, Vc is going to be at a maximum. And it's going to be somewhat like this. And that's why we say Vc lags the current. If we are going to graph the reactance X sub C versus the frequency by looking at the expression here, Xc is equal 1 over 2 pi Fc, which is, in other words, a constant over F. Our graph is going to look as a 1 over X graph. It's going to look like this. Now, another diagram we can look at is the dependence of the current on the frequency. And as you notice it here, remember, it's a capacitor. That's my AC source. This is the ammeter that's measuring the current, and that's the voltmeter across the capacitor. and as I change the frequency of the AC source, the current changes linearly. Now, where does that come from? You can get that by looking back at this equation. I is going to be VC over X sub C, and X sub C is 1 over 2 pi FC, so that's going to be equal 2 pi FC times VC, and you see the linear dependence on F.